See an example program using struct to understand when we might want to use struct. Let's write a program that calculates the area of a rectangle. We'll start by using single variables and then refactor the program until we are using struct instead. Let's make a new binary project with cargo called rectangles that will take the width and height of a rectangle specified in pixels and calculate the area of a rectangle. Listing 5-8 shows a short program with one way of doing exactly that in our project src main.rs. Okay, so I have taken this width and height, then calculating the width and height. Okay, now run this program. Okay, this code succeeds in figuring out the area of a rectangle by calling area function with each dimension, but we can do more to make this code clear and readable. The issue with this code is evident in the signature of area. The area function is supposed to calculate the area of one rectangle, but the function we wrote has two parameters, and it's not clear anywhere in our program that the parameters are related. It would be more readable and more manageable to group width and height together. We have already discussed one way we might to do that in the tuple type section of chapter 3 by using tuples. So here I have main.rs. Okay, so here they have width and height. In one way this program is better tuple. Let's add a bit of structure and we are now passing just one array, but in another way this version is less clear. Tuples don't name their elements, so we have to index into the parts of the tuple, making our calculation less obvious. Mixing up width and height wouldn't matter for the area calculation, but if you want to draw the rectangle on the screen it would matter. We want to keep in mind that the width is the tuple index 0 and height is the tuple index 1. This would be even harder for someone else to figure out and keep in mind if they were to use our code, because we haven't conveyed the meaning of our data in our code. It's now easier to introduce error refactoring with structs, adding more meaning. Where we use structs to add meaning by labeling the data, we can transform the tuple we are using into a struct with a name for the whole as well as name for the parts as shown in listing 5-10. So I have a struct rectangle. Okay, okay, and I'm borrowing that rectangle. Here we have defined a struct and named it as rectangle. Inside the curly brackets we define the fields as width and height, both of which have type u32. Then in main we created a particular instance of rectangle that has a width of 30 and a height of 50. Our area function is now defined with one parameter which we have named rectangle, whose type is an immutable borrow of a struct rectangle instance. As mentioned in chapter 4, we want to borrow the struct rather than taking the ownership of it. This way main returns its ownership and can continue using rect1, which is the reason we use the ampersand in the function signature, where we call the function the area function accesses the width and height fields of the rectangle instant. Note that accessing fields of a borrowed struct instant does not move the field name, which is why you often see borrows of struct. Our function signature for area now says exactly what we mean. Calculate the area of rectangle using its width and height fields. This conveys that the width and height are related to each other, and it gives descriptive names to the values rather than using the tuple index values of 0 and 1. This is a win for clarity. Adding useful functionality with derived traits, it would be useful to be able to print an instance of a rectangle while we are debugging our program and see the values for all its fields. Listing 5-1 tries using the println macro as we have used in previous chapter. This won't work, however. File name src main.rs struct rectangle width and height, let rect equal to rectangle width colon 30 height colon 50. When we compile this code we get an error with the core message. The println macro can do many kinds of formatting, and by default the curly bracket tells println to use formatting known as display output, intended for direct end user consumption. The print types we have seen so far implements display by default because there's only one way you would want to show sorry one or any other primitive type to a user, but which structs the way println should format the output is less clear, because there are more display possibilities. Do you want commas or not? Do you want to print the curly bracket? Should all the fields been shown? Due to this ambiguity, Rush doesn't try to guess what we want, and struct doesn't have provided an implementation of display to use with println and the placeholder. If we continue reading the error, we will find this helpful note. Let's try it. The println macro will now look like println rect1 colon rect1. Putting the specifier inside the curly bracket tells println we want to use an output format called debug. The debug traits enable us to point our struct in a way that is useful for developers, so we can see its value while we are debugging our code. Compile the code with this change. We still get an error, but again the compiler gives us a helpful note. Rush does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for our struct. To do so, we can add the outer attribute just before the struct definition as shown. Okay, so this derived debug. Now when we run the program, we won't get any errors. Nice. It's not the prettiest output, but it shows the values of all fields for this instance, which would definitely help during debugging. When we have large struct, it's useful to have output that's a bit easier to read. In those cases, we use the colon hash question mark instead of colon question mark. Okay, another way to print out a value using the debug format is used to use the dbg exclamation macro, which takes ownership of an expression, as opposed to println that takes a reference. Oh, okay, println takes only a reference. Here's an example where we are interested in the value which gets assigned to the width field, as well as the value of the whole struct in rect1. Okay, we can put debug around the expression, and because debug returns ownership of the expression value, the width field will get the same value as if we didn't have the debug call there. We don't want debug to take ownership of rect1, so we use a reference to rect1 in the next call. Here's what the output of this example looks like. We can see the first bit of output comes from src main.rs line 10, where we are debugging the expression 30 into scale, and its resulting value is 60. The debug format implemented for integers is to print only their value. The debug call on line 14 of src main.rs outputs the value of ampersand rect1, which is the rectangle struct. This output uses the pretty debug formatting of the rectangle type. The dbg macro can be really helpful when you are trying to figure out what your code is doing. In addition to the debug trait, Rust has provided a number of traits for us to use with a derived attribute that can add useful behavior to our custom types. Those traits and their behaviors are listed in Appendix C. We will cover how to implement these traits with custom behavior, as well as how to create your own traits in Chapter 10. These are There are also many useful attributes other than derived. For more information, our area function is very specific. It only computes the area of rectangles. It would be helpful to tie this behavior more closely to our rectangle struct, because it won't work with any other type. Let's look at how we can continue to refactor this code by turning the area function into an area method defined on our rectangle type. Okay, let's cover this as well. Method syntax. Methods are similar to functions. We declare them with the fn keyword and a name. They can have parameters and a return value. They can contain some code that's run when the method is called from somewhere else. Unlike function, methods are defined within the context of a struct or an enum or a trade object, which we covered in chapter 6 and 17 respectively, and their first parameter is always self, which represent the instance of the struct the method is been called on. Defining method, let's change the area function that has a rectangle instance as a parameter and instead make an area method defined on the rectangle struct as shown in listing 5-13. So I have a rectangle struct and I'm implementing, the impl keyword is like you can implement methods for this particular struct. So I have an area method, so I can call rect1 dot area. Okay, and a small self means it can take the object of the struct, but if it is a capital self, that means we are creating the object of the struct. To define the function within the context of a rectangle, we start an impl implementation block for rectangle. Everything within this impl block will be associated with the rectangle type. Then we move the area function within the impl curly brackets and change the first, and in this case only parameter to be self in the signature and everywhere within the body. In main, where we called the area function and passed rect1 as an argument, we can instead use method syntax to call the area method on our rectangle instance. The method syntax goes after an instance we add a dot followed by the method name, parenthesis, and any arguments in the signature. For area we use ampersand self instead of rectangle colon ampersand rectangle. The ampersand self is actually short for self within an impl block. The type self is an alias for the type that the impl block is for. Method use methods must have a parameter named self of type self for their first parameter. So let's Rust lets you abbreviate this with the only name self in the first parameter spot. Note that we still need to use the ampersand in front of the self shorthand to indicate that this method borrows the self instance, just as we did in rectangle. Methods can take ownership of self, borrow self immutably as we have done here, or borrow self mutably just as they can any other parameter. We have chosen ampersand self here for the same reason we have used ampersand rectangle in the function version. We don't want to take ownership and we just want to read the data in the struct, not to write to it. If we want to change the instance that we have called the method, or as part of what the method does, we would use ampersand mute self as the first parameter. Having a method that takes ownership of the instance by just using self as the first parameter is rare. This technique is usually used when the method transforms selves into something else and you want to prevent the caller from using the original instance after the transformation. The main reason for using methods instead of function, in addition to providing method syntax and not having to repeat the type of self in every method signature, is for organization. We have put all the things that we can do with an instance of type in one impl block, rather than making future users of our code search for capabilities of rectangle in various places in the library we provide. Now that we have choose to give a method the same name as one of the structs field, for example we can define a method on rectangle also name width. So impl rectangle fn width function main. Okay, here we are choosing to make the width method return true if the value in the instance width field is greater than 0, and false if the value is 0. We can use the field within a method of the same name for any purpose. In the main, when we follow rect1 dot method width with parenthesis rush knows we mean the method width. When we don't use parenthesis rush knows we mean the field width. Often but not always, when we give methods with the same name as a field, we want it to only return the value in the field and do nothing else. Method like this are called getters, and Rush does not implement them automatically for structs field as some other languages do. Getters are useful because you can make the field private but the method public, and thus enables read-only access to that field as part of the types public API. We will discussing what public and private are and how to designate a field or method as public or private in chapter 7. Where is the arrow operator in C and C++? Two different operators are used for calling methods. You use dot if you are calling a method on the object directly, and the arrow if you are calling the method on a pointer to the object and need to dereference the pointer first. In other words, if the object is a pointer, object arrow something is similar to star object dot something. Rust doesn't have an equivalent to the arrow operator. Instead, Rust has a feature called automatic referencing and dereferencing. Calling methods is one of the few places in Rust that has this behavior. Here is how it works. When you call a method with object dot something, Rust automatically adds in ampersand or ampersand mute or star so object matches signature of the method. In other words, the following are the same. Okay, the first one looks much cleaner. The automatic referencing behavior works because methods have a clear receiver, the type of cell given the receiver and name of a method. Rust can figure out definitively whether the method is reading ampersand self, mutating self, or consuming self. I think this feature is kind of like Golang. The fact that Rust makes borrowing implicit for method receivers is a big part of making ownership ergonomic in practice. Methods with more parameter. Let's practice using methods by implementing a second method on the rectangle struct. This type we want an instance of rectangle to take another instance of rectangle and return to if the second rectangle can fit completely within cell the first rectangle, otherwise it should return false. That is, once we have defined that can hold method, we want to be able to write program shown in listing 5-14. Okay, and the expected behavior would look like the following. Because both dimension of rect2 are smaller than the dimension of rect1 but rect3 is wider than rect1, we want to define a method, so it will be within the impl rectangle block. The method name will be can hold and it will take an immutable borrow of another rectangle as a parameter. We can tell what the type of the parameter will be by looking at the code that calls the method and passes an ampersand rect2, which is an immutable borrow to rect2 an instance of rectangle. This makes sense because we only need to read a rect2 rather than write, which would mean we would need a mutable borrow, and we would want main to retain ownership of rect2, so we can use it again by calling the can hold method. Sorry, the return type of can hold will be a boolean and the implementation will check whether the width and height of self are both greater than the width and height of other rectangle respectively. Let's add the new can hold method to the impl block from listing 5-13 shown in listing 5-15. When we run this code with the main function in listing 5-14, we will get our desired output. Methods can take multiple parameters that we add to the signature after the self parameter, and those parameter work just like this parameters in function. Associated functions, all functions defined within an impl block are called associated function because they are associated with the type named after the impl. We can define associated functions that don't have self as their first parameter and thus are not methods because they don't need an instance of the type to work with. We have already used one function like this, like the string colon colon from function that defines on the string type. Associated functions that aren't methods are often used for constructor that will return a new instance of the struct. These are often called new, but new isn't a special name and isn't built into the language. For example, we could choose to provide an associated function named square that would only have one dimensional parameter and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. The self keyword in the return type and in the body of the function are aliases for the type that appears after the impl keyword, which in this case is rectangle. To call this associate function, we use the uh, double colon syntax with the struct name. Let's sq equal to rect colon colon square is an example. This function is namespaced by the struct. The double colon syntax is used for both associated function and namespaces created by modules. We will discuss module in chapter 7. Each struct is allowed to have multiple IMPL blocks. For example, listing 5-15 is equivalent to the code shown in listing 5-16, which has each method in its own IMPL block. There's no reason to separate this method into multiple IMPL blocks, but this is valid syntax. We will see a case in which multiple IMPL blocks are useful in chapter 10, where we discuss generic types and traits. Structs lets you create custom types that are meaningful for your domain. By using struct, you can keep each associated pieces of data connected to each other and name each piece to make your code clear. In IMPL blocks, you can define functions that are associated with your type and methods that are kind of associated function that let you specify the behavior that instances of your structs have. But structs aren't the only way you can create custom type. Let's turn to Rust enum feature to add another tool to your toolbox. So yeah, we will see about enum in the next video. Thank you for watching. Bye.